Let's start the class on statistical inference and analysis of data variability. So in this lecture, we'll mainly talk about ANOVA, so introduction to ANOVA, the procedure for ANOVA, and one-way ANOVA. So let's start with introduction. So what do we mean by analysis of data variability? So in the last class, we discussed the concept of trying to understand how can we do hypothesis testing for two variances and a single variance. So what we are trying to extend this concept here is, what if we have more than two groups? So let's say if we have more than two, what do we do then? So the idea here is to try and develop a method so that we can compare the variance or anything that represents more than two groups. So an outcome variable is generally represented by a set of measured values that result from an experiment or some other statistical process. So there are two types of variables that we're going to talk about. One is an outcome variable, one is an explanatory variable. So an outcome variable is basically a set of measure values that you get from an experiment or some other statistical process. And an explanatory variable, the name itself says it, it's an explanation. On the other hand, is a variable that is used for predicting the value of the outcome variable. So you can always think of two variables here. One variable is the outcome, the other is the explanation. So you have two different variables. One is the independent variable, one is the dependent variable. So outcome variables are generally also called dependent variables. Explanatory variables are also called independent variables. So let's talk more about them. So a linear model, whenever we talk about these two, so we also have to think about two values. So we have, let's say we have two values. So an outcome variable, let's say we call it y, and an explanatory variable x. So we can represent them in different models. So let's use one type of model, which is a linear model. So it basically says that the parameters are linear to define the model, and we can represent such models like this: yj equals beta naught plus beta 1 x1j, beta 2 x2j, plus and so on, beta k xkj, and epsilon j. So where beta j here represents the coefficients in the model and epsilon j represents the random error. Remember that any type of model will always have some form of random error that is always present inside the model. So to use this to analyze these kinds of linear models and to check whether both groups are from the same party or not, we generally use a ANOVA procedure. So what is ANOVA? So ANOVA in its expansion is the analysis of variables. So it's the analysis of variables. And how do we define it? So it's a technique where we try to understand whereby the total variation present in a set of data, we split it into two or more components. So associated with each of these components is a specific source of variation, so that in the analysis it is possible to ascertain the magnitude of contributions of each of these sources to the total variation. So think of it this way. So let me put an analogy to this. So let's consider that the total variation is this. So let's say I represent this total variation by a rectangle. Now if I try to split this into parts, so what we are doing in ANOVA is we have a total variation and we split it into two or more components. So let's say I have 1, 2, 3, and 4. So we have 4 different components. What we want to do is, how much is each of these contributing to the total variation? So how much is 1 contributing to the total variation, how much is 2 contributing, how much is 3 contributing, and how much is 4 contributing to the total variation. So this is basically the best example of analysis of understanding how ANOVA works. Now let's say if all of them are equally contributing to it, we consider that all of them have a significant effect on the total variation. Let's say if one of them does not contribute enough, then we can say that at least one of them does not have enough contribution to the total variation. So what are the applications of this? So the most common applications is to test the hypothesis and estimate the hypothesis about population variances, and also to estimate and test hypotheses about population means. So what does this mean? So let's say if you have a hypothesis of 3 or more groups, so let's say you have 2 or more groups that are, so let's say I have one group here, 2 and 3. So if we want to test whether the variances of all these groups are the same, or whether the population, so whether these variances are from the same population, or whether their mu's are from the same population or not. So to ascertain this particular understanding of what so is basically we use ANOVA. So ANOVA is basically an expanded version of the 2 sample t-test that we have done. But what we do here is we can also apply this to we can apply this to 2 groups or more groups. So that's the reason why we represent the term 2 or more components. Now, what is the procedure of ANOVA? So this is the basic steps in the procedure of ANOVA. Let's start with the first one, description of data. So the simplest type of analysis of variance is what is called as one-way ANOVA. So in which we are only trying to have one source of variation or factor that we are trying to investigate. So it's an extension to the 3 or more samples of the t-test procedure for use with 2 independent samples. So we already talked about this in the previous lectures, t-test for 2 independent samples. So where we talked about we have one sample, sample 1, and we have sample 2. So we had mu1 for this, and we have sigma 1 for this. We had mu2 for this and the sigma 2 for this. What we were trying to do is whether we were trying to ascertain whether both of them have the same mean and variance, or they have different means and variance depending on the conditions under which we are trying to examine this. So if we talked about the test of variance, we were just testing the alternative hypothesis was that sigma 1 square is not equal to sigma 2 square, and the null hypothesis was the sigma 1 square is equal to sigma 2 square. If we were testing means, we were talking about h0 being mu1 equal to mu2 and ha being that mu1 is not equal to mu2. So this was the test of means, and the other was the test of variance. So we already discussed these 2 types before. What if we have more than 2 samples? How would you do that then? So that is where one-way ANOVA comes in. So here we're only using one source of variation, and we are trying to extend this to 3 or more samples. So in a typical situation, what would we try to do here is that we want to use one-way analysis of variance to test the null hypothesis that 3 or more treatments are equally effective. So the necessary experiment designed in such a way so that the treatment of interest are assigned completely at random to the subjects to determine the treatment effectiveness are made. So for this reason, this is basically called as a completely randomized experimental design. So let me put it in much more explanation here. Let's say I have 4 treatments. So let's say we have 4 drugs, and we are trying to check whether these are going to work or not. Let's say I have 16 samples. What am I going to do with 16 samples here is that I'm going to randomly assign them into 4 groups, and let's call this the drugs A, B, C, and D. For the first 4, I'm gonna assign drug A, drug B for the next one, drug C for the next one, and drug D for the next one. Now the priority here is to remember that this process of trying to split the 16 samples into 4 groups is completely random. So what are we doing here in this completely random process is that, so it's completely randomized. So let's say for example we ask each of them to draw a number, and we assign their group based on what they draw. right? So this is an example of a completely randomized experimental design. So we have 4 drugs. Now, what would be the H0 and what would be HA? What would be the null hypothesis and what would be the alternative hypothesis? So let's say H0 represents that all 4 treatments are equally effective. So we are basically saying that all 4 treatments are equally effective, no one is better than the other. So HA basically says that some treatment are better than others. So in this particular process, we know that we have 4 samples in each group, right, who are assigned with each drug. The variations that are present here can be 2 types. They can be between drugs or between treatments or within the samples. So let me, what does this mean? Let's say this 4, let me call them 1, 2, 3 and 4. All 4 are not going to show the same effect. This represents the variation within samples. So you have a sample and the variation that is present within the sample is called as the within sample variation. And you have another type of variation where there is a variation between each different type of sample. So we have samples themselves that are completely different from each other, and we are expecting to see some variation between samples. So we have 2 types of variations here. So we have the variations that are within a sample, and we also have the variations that are between samples. So these are the samples that we have. So if they are between samples, we call them between sample variation, and if they are within the sample itself, we call them within samples variation. So we are going to use these 2 a lot in ANOVA. So keep this in mind when we are talking about ANOVA. So we are going to discuss this, we are going to come back to this again. So let me continue with this. So now you remember the concept of completely randomized experimental design, where we only have 1 treatment and we are expecting outcomes. So there is only 1 factor. The factor itself is the treatment. So there is only 1 factor that can affect that particular outcome that is going to be generated. So this is a sample experiment of, this is a sample values for completely randomized design. So for example, you can take, let's say we have 4 antihypertensive drugs, and we have 16 samples, right? So let's say, for example, each treatment is A, B, C and D. So let me call these treatments, and in each of them you notice that we have to split this into 4 samples. So which means that there are 4 of them. So let's say, for example, we are trying to test, the test here is to test their blood pressure. Let me call it systolic blood pressure, right? And we have values, for example, let's say 112, 114, let's say 118, 132, and let's say 115, 152, 113, 102, right? Let's say, for example, 102, 153, 114, 171, and you have 105, 122, let's say 128, 135. So these are the values for the systolic blood pressures of each of these treatments. So this type of marking here is basically called as a completely randomized block design. So this is an example of a completely randomized block design where we are testing the systolic blood pressure with 4 antihypertensive drugs, and we have taken their blood pressure, and we are testing basically their systolic blood pressure by after using the 4 antihypertensive drugs for, let's say, for patients with hypertension. So all of the people that we have here are the ones that have hypertension. So what would be the experimental design we call here? So this is a randomly, so we have assigned the treatment randomly to all of them. So this would be a completely randomized design. So we have split them into groups, and we have split them, and we have gathered the values for their hypertension by using the variable systolic blood pressure. Remember that this is the only factor. So this is a single factor that we are using to judge whether the treatments are effective or not, right? So this is an example of a table of how you would do ANOVA for using a single factor. So we have 10 steps in the hypothesis testing. The first one would be the description of data. Again, remember here that these are generic. So the first one is Xij, representing the ith observation resulting from the jth treatment. So best example of looking at this would be, let's say, this would be sample 1, 2, 3, 4, right? So we would call this X1A, right? So the first sample with A treatment. This would be X1B. This would be first sample with B treatment, first sample with C treatment, third sample. This would be, for example, X third sample with C treatment, right? Now we have two values to remember here. One is Nj and one is K. K represents the number of samples. N represents the number of observations in each sample. So here we have 4 observations in each sample. So Nj would be 4, and we have 4 samples. So this would be 4. So this is how you would understand the values Nj and K. Now, what are the values, the other values that we are going to find? The next one is the total for J treatment. So what we are going to try to find is, we are going to find the mean of each of these samples. So we are going to call them X bar A, X bar B, X bar C, X bar D. Right? So this would be the values that we are going to find. And we are also going to find another mean which represents the total, or what we call as a grand mean. So mean of all observations. So this would be the T double dot, which is the total of all observations that we have, and X double dot representing the T double dot by N. So this is the total here. So one values to remember is, remember the values N representing the total number of observations, right? So total number of observations, and Nj representing the total number of observations in a treatment, and K representing the total number of treatments. So these are the values that we do have here. Now, what are the assumptions that we have taken? So before stating the assumptions, so let us specify the model for the experimental design here. So the one-way analysis of variance model, we can write them as Xij equal to mu plus tau j plus epsilon j. So mu here represents the mean of all K population means, and is also called as the grand mean, which is represented by X double dot or X double bar. Tij represents the difference between the mean of the jth population and the grand mean. So this is called as also called as the treatment effect, and epsilon j represents the amount by which an individual measurement differs from the mean of the population. It's called as the error term. So let me mention this, what this means here. So what does tau ij represent here? So we represent the grand mean here So tau ij represents grand mean minus mean of a treatment. Epsilon ij represents the observation minus the mean of a treatment. So best way to look at this is the concept of between samples, and this is the concept of within samples. So we have between samples and within samples. So we are looking at the effect of both of these on the value of the observation or the one-way analysis, right? What is the hypothesis here? So we are basically testing the null hypothesis that all population treatment means are equal against the alternative that basically says that at least one pair are not equal. So we can write this as h naught equal to mu1 equal to mu2 equal to mu k, and ha represents not all mu j are equal. Again guys, this does not mean that all of them are unequal. It means that at least one. So at least one mean is significantly different, right? So this is what the hypothesis basically says in terms of the alternative hypothesis. Now if all of them match, then the observation of all 10 of them will be on the same line. If they do not match, we have different groups with different variations. So this is the pictorial representation of this is the alternative hypothesis, and this is the null hypothesis. So this is a picture of the representation of the null hypothesis, and this is the representation of an alternative hypothesis. Now let's say if the means are equal, then we are trying to see whether the each treatment effect is equal to 0. So h naught represents tau j equal to 0, and ha represents that not all tau j are equal to 0, right? So this is basically the concept of tau j here. Now next, what is the statistic that we are going to use here? So we also use this particular statistic before. Because we are testing the variance, we are going to use a statistic called the variance ratio, right? So variance ratio represents the variance, right? So let's say sigma 1 square by sigma 2 square, but here it represents a different thing. We have two types of variations. Before, I already talked about this. We have two types of variations. One variation is between samples, and the other variation is within samples. So the variance ratio represents between samples variation divided by within samples variation. This is the statistic that we are going to use to judge whether to accept the null hypothesis or to reject the null hypothesis. Now, how would we represent this value? What is the statistic used to distribute? So the distribution that it uses is going to be, so the distribution that this particular the one that this uses is going to be an F distribution. So where when h naught is true, we have all the assumptions met. Now in general, the decision rule is to reject the null hypothesis if the computed value of the variance ratio is equal to or greater than the critical value of the F distribution chosen. So let's say we have the F distribution here. So let me draw this a little more clear. The reason again we use F distribution, guys, remember that this is a ratio. Ratios are never less than 0. So ratios have an absolute 0. They do not have any negative values. The only observations that fit this is the F distribution. Now, if we have a specific value, let's say alpha here, if this particular region represents alpha, let's say for example 0.05, Now this is the critical value for F, right? So this is also called as the F, the table value. Now if the value that we get, or the calculated value, is greater than the table value, we can reject H0, right? So the other option would be, if the calculated value is less than the table value, then we can accept H0, right? So remember this, that when the F calculated value is less than the table value, then we accept H0, and if the F calculated value is greater than the F table value, we reject H0. So remember here that when we calculate the F value for the table, remember that F table contains 2 degrees of freedom. So remember this 2 degrees of freedom. So we're going to come back to this again when we solve the problem. So how would you calculate this F value here? So we said that we have 2 variances, between samples and within sample variance. So how would you calculate each of these variances? So we use a specific method called as the ANOVA table. So what is the ANOVA table here? So let's talk about all the terms that we are going to use in the ANOVA table. So ANOVA table, the first one is the total sum of squares. The name itself says it's the sum of squares of the deviations of individual observations from mean of all observations taken together. So we have a single observation xij, and we have the grand mean. So if we square it and sum up all those values, then this value represents the SST, or the total sum of squares. Now the next one is within sum of squares. Again, remember guys, whenever we say the term within, it's going to be the observation minus the mean of a sample, right? So we have xij minus x bar of j, right? If we square it and sum it up all, then that represents the within group sum of squares, represented by SSW. And the last one, among group sum of squares, also called between group sum of squares. We can also call between, right? It doesn't make a difference. So here, remember that between represents the difference between the mean of a treatment or sample minus the grand mean. So we have x bar of j minus x double bar square, and if we sum all of them up, that gives you the value for the between groups or the among group sum of squares, represented by SSA. Now what do we do with all these values? So one way to check whether your answers are correct or not is to remember that the total sum of squares is the sum of the among group sum of squares and the within group sum of squares. Now once we have these values, so what do we do here? So once we have these values, we construct an ANOVA table. So what will ANOVA table contain? So we have the sum of squares values, we have the degrees of freedom, and then we also have what we called as the mean square value. So remember this value is ms, right? So we have the first one that we have here is the among group sum of squares, and then the within group sum of squares. Next we also have the total sum of squares. So let me write this separately because that would be irrelevant to this particular table. Now how would you know what is the degrees of freedom for the among group sum of squares? So when we talk about among groups, so what does this mean here, among groups? So we are basically saying that we have two specific values that we have to consider, that is the samples itself, right? So remember that the degrees of freedom is always going to be whatever is the number of them present minus 1. So because we are testing among groups themselves, so we know that the number of groups are k, so degrees of freedom would be k minus 1. So this would give you k minus 1. Next, within groups, so which means that we have two values that we are considering. So one value is n, small n, minus, and then we also have the values for the samples. So we have the total number of observations. So let me write this way. So within groups, which is observations minus the treatment. So we know that the number of treatments or the number of groups is k and the number of observations is n. So we can just write directly n, total number of observations, minus k. So the total sum of squares will be n minus 1. Again, this is pretty evident because the total number of observations is n. So minus 1 will always be the degrees of freedom. Now, how would you calculate the mean square? So remember that ms represents mean square. We have two values here, msa and msw. msa representing the mean square among values, and we have mean square within values. Now, MSA is going to be the total sum of squares divided by k minus 1. So sum of squares divided by the degrees of freedom, and mean squares within will be SSW by n minus k. Now we have the mean sum of squares. Now let's calculate the F calculated or the variance ratio. So how would you calculate this? Remember that these are the squares or sum of squares. So just the F calculated is going to be the among mean square divided by mean square within. Now we also have another value, which is the table value. I told you just a minute ago that we have 2 degrees of freedom to take, right? So remember that this is the samples and this is the error. Every time you remember this, that whenever we have the among groups, we are trying to talk about samples, and when we have within groups, we are trying to talk about the error that is within each group, right? So df1 has the same df as k minus 1. So the df1 value will be k minus 1, and the df2 value will be n minus k. So F of the table, the degrees of freedom will be k minus 1 and uppercase n minus k. Now if this calculated value is greater than the table value, we reject H0, and vice versa. If the calculated value is less than the table value, we accept H0. So we have 2 separate values right here. So one representing the fact that we have F calculated, we reject. So H0, if calculated, is greater than the table, and if the calculated is less than the table, we accept H0. So now this is how you calculate the ANOVA table and how you write down the ANOVA table. Now when we reject the H0, we can conclude that not all population means are equal. Now if we fail to reject H0, which basically represents the fact that we are accepting H0, we conclude that populations means are not significantly different from each other. Remember this, guys. Whenever we talk about the 2 parts here, we have to write a conclusion. This conclusion, we write it if the calculated value is less than the table value. This particular one we write when the calculated value is greater than the table value. So which means that this we write it when we reject H0, and this we write when we accept H0 or we do not reject H0. So the same thing can be said two ways. We accept H naught or we fail to reject H naught. So this is how you determine the values. We can also find the p-value from the f-value calculator. So let's start with the small problem, and let's try using this problem to understand the entire process under which we just talked about right now. Again, it might seem a little bit redundant knowing all this terminology, but it's very easy to solve when you start solving these problems. So let's start these problems. So we have what is given here. So you have male and female rats were given a hypnotic drug, and the number of minutes they slept in minutes are recorded. Ascertained by ANOVA if females slept longer than males. So the first things first, we have the data. First things first to write down is to write down the hypothesis. So let's start with the hypothesis. So what is the hypothesis given here? We have H naught and we have HA. So H naught is that we have male rats and we have female rats. So they have asked us to judge whether female rats sleep longer than male rats. So mu m less than mu f, mu m equal to mu f. Again, it doesn't matter whether you write m in front or f in the back. You can also write this as mu f equal to mu m, or we can also write this as mu f greater than mu m. It doesn't matter how you write it. You just have to make sure that you write the actual hypothesis that they're asking you to test. So remember that they're asking you to test whether females slept longer than males. So just write down the values. Again, we have two groups here. So the total number of samples is 2. Now, the total number of observations so that is 1, 2, 3, 4, 5. So there's 2 of them, so 10. And the number of observations in each of them is around 5 of them. So you have 5 observations in each of them. Now, so let's start with the problem right here now. Now let's go through the data. What is given here? So let me just copy this data right here. We have the data. So they have given us in minutes the male and female, the amount of time they've slept. So you have 13, 16, 19, 14 and 16. So you have 13, 16, 19, 14 and 16. Next you have 20, 17, 22. Next you have 24, 19. Again, so this is a simpler process. So let's start with the males. So remember that we have to find 2 means. So we have means right now. So what are the means that we have to find? So we have x bar of the males, x bar of females, and x double bar. So the mean of males, the mean of females, and the total mean. So let's start with each of these means right now. So you have 13 plus 16 plus 19 plus 14 plus 16 divided by 5, and you also have 20 plus 17 plus 22 plus 24 plus 19 by 5. Again, so you have x double bar, so which is the sum of all the observations that we have right here. So now let's try to calculate these values again. I'm not gonna calculate them using a calculator. So I have the values right here, so let me write them down. So XM is 15.6, XF is 20.4, and X double bar is 18. Now we have the data right here, which is the means. Now remember guys, we have to find out the values right here. So the first one, so let me write it as sum of squares. So this is what we have to find right here. So the first one that we have to find is sum of squares among, and sum of squares within, and sum of squares total. So what would be sum of squares between? So remember that we have the samples we are trying to find within, which means that we are trying to find between male and the grand mean. So we have 5 of these observations times the mean for the males is 15.6 minus you have, so let me write this down as a formula so that you guys can remember this. So the number of males times x bar of m minus x double bar square plus the number of females times x bar of f minus x double bar square. So this is pretty evident right here. The number of males is 5. All right, let's continue here. So x bar of m here is 15.6 minus 18 square plus 5 times we have 20.4 minus 18 square. Now, so this value when calculated would be 57.6. Now, what would be within sum of squares? So within sum of squares is going to be sigma, which is the summation of all the values, the individual observations, so xi minus x, so let me call this xm bar square, right? So you have the values minus this particular value. Let me call this xim minus x bar m plus sigma xif minus x bar f square. So how would we write this now? So let me go through these values right here. So this would represents the sum of squares within. So this value when you calculate it will give you 50.4. So I've split this into black and blue. So black represents the observations for the male and the blue represents the observations for the female. Remember that we are taking the observation of the particular group and we are subtracting it from the mean of that particular group. Remember that this is a within, so which means that within these samples, so we have the observation for the in that particular sample minus the mean of that sample. So we're just trying to find the variation in that. Next, the last one would be SST, which is the total sum of squares. So this value basically is all the observations minus the grand mean squared. So let me write down these values for you. So this value represents the SST here. So the SST value here would be 108. So the easiest way to check this, just add both of these values. So 57.8 and 50.4. So we know that SST is SSA plus SSW. So 50.4 plus 57.6. So this also again gets back to the value 108. So you can either find it this way or you can directly calculate the SST. So by calculating this, you check whether your samples SSA and SSW are right or not. Now we have all the values. Now let's try and construct the ANOVA table. So what would be the ANOVA table look like here again? So the source of variation, so is it between the samples or within the samples, or you can simply write it as SS, the sum of squares. We have the degrees of freedom, right? So we have, let me write it separately, SS, the degrees of freedom, and we have the mean square and the variance ratio. So we have among, or so let me write it as among samples and within samples. So let me split this so that we can understand this better. So we have the total at the end. So now let's start filling in the values. So the among samples, SSA is 57.6 and within samples is 50.4 and the total is 108. So DF, the number of samples. So the number of samples here is, so we know that the total number of samples is 2. We know that DF among samples is K minus 1. So which can be written as 2 minus 1, which is going to be 1. Now we also have within samples, which is going to be N minus K. We know the total number of observations are 10 minus there are 2 samples in it. So we have 8. So, and the total will be 9. Now MS is going to be 57.6 by 1 and 50.4 by 8. So this value again will stay the same. So let's keep it same, 57.6, and 50.4 divided by 8 will leave you 6.3. Now the variance ratio is MSA over MSW. So which is 57.6 divided by 6.3. So this value we can calculate it to be 9.1428. So this is the variance ratio for this particular sample right here. Alright, so we have the variance ratio. So we also know that this can be represented as the calculated value for F. Now, so let's try and understand this particular F calculated value, which is 9.1428. Now we have to calculate the table value. So here we have DF1 as 1 and DF2 as 8. So we have to calculate the F table value at alpha equal to the normal values for so when you don't see a particular alpha value in the question, just use 0.05 or 5%, which is the most common one. So we have alpha equal to 0.05, 1 and 8. So let me go to the table. So this is a nice table of the F critical values. So let's try and understand the F table here. So you have 2 values to determine. One is we have the degrees of freedom in the numerator and we have the degrees of freedom in the denominator, representing that this represents DF1 and this represents DF2. Now we have DF2 of 8 and DF1 of 1. So we have DF2 of 8 and DF1 of 1, and the p-value that we chose is 0.05, so that value is 5.32. So again, note down, F values are the same throughout the entire table, so this value will give you 5.32. Now the calculated value of F here is 9.1428, and the table value that we have is 5.32. Remember that the table value represents the critical value. So we have, so if you draw an F distribution right now, so we have an S distribution right here, and this is an F distribution. And this is the critical value right here. This region represents alpha, and the value we have is 5.32, and 9.148 is somewhere right here. So now we can pretty much say that the calculated value of F is much greater than the table value. So which means that we can reject H0. So what did H0 say? H0 said that the mean of the males in the terms of the number of minutes slept is the same as that of the females. So if we reject H0, the HA that we used here is mu M is less than mu F. So what can we conclude here? So we can conclude that female rats slept significantly longer than male rats, right? So female rats slept significantly longer than males. So this is the conclusion that we get when we reject H0. Now the term significantly here represents the fact that we are trying to justify this using statistical measures. So remember this whenever you solve problems. So whenever you have this type of problems, we are always trying to understand whether this particular sample that we have chosen has to be statistically significant in terms of whatever the hypothesis that we choose. So this is an exercise for you guys. So we have the problem: average voice pitch for male and female participants is given below. Ascertained by ANOVA if female participants have a higher pitch than male participants. So we have the three values right here. So the K values is 2, the total number of observations is 6, and we have 3 observations in each of them. Again, we are going to find the male, the female, and you're going to find the grand mean. Then you're going to find the sum of squares among, sum of squares within, and sum of squares total. So once we find this particular values, then try and ascertain by using the ANOVA table. So with that, I end the lecture on the first part of ANOVA. So in the next lecture, we're going to continue this topic, and we're going to talk about two-way ANOVA, and we're going to talk about another type of experimental design called as a block design. So I'll see you in the next lecture.